Welcome all of you. Since the last two classes we discussed about nuclear overhazer effect, the concept, basic concepts. I told you what is an NOE. You will see the enhancement in the intensity of the signal or of course reduction in the intensity, both are possible. One of the spin is irradiated with a low RF. And basic condition, it need not be scalar coupled. I told you basic requirement is they should be spatially close to each other. Spatial proximity is important condition to observe NOE. And we discuss various parameters which are responsible for this NOE. I said NOE depends upon the internuclear distance. It depends upon the magnetic field at which we are going to study, because it depends upon the correlation time. In addition to that, it depends upon the pathways available for relaxation. Then we discuss about double quantum, zero quantum and single quantum relaxation pathways, and what will happen to the signal intensity when the spins adapts double quantum relaxation pathway, or the cross correlation is because of zero quantum pathway. In double quantum there is enhancement in the intensity, in the zero quantum there is a reduction in the intensity by 50%. We saw that. And zero, of course, single quantum will not give rise to any NOE. And of course, this dipolar relaxation is the main reason for observing NOE. Then the question is, where are these fluctuating fields which is coming for the spins to relax? The spins will relax through dipolar interactions, and there must be a fluctuating field for that. This also we discussed about interaction, dipolar interaction. I said if they have two spins close to each other, molecule may be undergoing tumbling. The orientation of the spins with respect to the magnetic field do not change. However, diagrammatically I showed you, when the spins are undergoing motion, undergoing rotation or changing the position, one spin will introduce or create oscillating magnetic field at the site of the other spin. Of course, vice versa. And these oscillating fields are responsible for the spins to relax. That's what I said. Then the question is, these are the origin of the spins to relax, and we discuss about the fluctuating magnetic fields. So these fluctuating magnetic field releases energy, and of course when the molecules are fluctuating, undergoing motion to create a fluctuating magnetic field, there is a term called rotational correlation time, which I said yesterday. And of course we discussed about the spectral density function also. Spectral density function depending upon Larmor frequency and the correlation time, I said. The correlation time, now I will start from today, the correlation time. It tells about the motion of the molecules here, and the correlation time is defined as Tc. It correlates the orientation of molecule at two different times and depends upon several factors. In principle, it is time required for the molecule to undergo one rotation by 1 radian. That is the definition. But anyway, basically this is the important thing you understand. And of course, it depends upon the molecular weight. Obviously, when the molecules are undergoing tumbling, it depends upon the size or weight of the molecule. And this is the reason I will say the correlation time tau c defines the sluggishness of the molecule. A short correlation time means fast random motion. A long correlation time means sluggish motion of the molecule. Hello, I am going to stop here because I need a pen. Okay, I got the pen. All right. A long correlation time means sluggish motion of the molecule. Let us see, small molecules tumble more quickly here. I can see that. These are the small molecules. These are large molecules. They tumble more slowly. These molecules tumble very quickly. And we can make a rough estimate of the correlation time for a given mass, depending upon the mass of the size of the molecule or its molecular weight. This is if the molecular weight is given by mR, and this is the rough estimate to tell you what should be the correlation time. Of course, it can be different, but it is an estimate. If I know the molecular weight, this has to be multiplied by 10 to the power minus 12 seconds, then I know what is the correlation time in nanoseconds. So all these things, one is molecular motions are within nanosecond scale. I can make a rough estimate based on that. And just for an example, if I take a 3.3 kilodalton size of the molecule, it's a small protein or whatever it is, then the correlation time I can calculate as 2 nanoseconds. That means you can find out what is the resonating frequency. It should, or not resonating frequency, just frequency. Because if I once I know the correlation time, once I know 2 nanosecond, 1 over inverse of 2 to the 10 to the power of minus 9, we can find out that turns out to be 500 megahertz. Okay. So that is the frequency of correlation time for a particular molecular weight. Motions with higher frequency will be generally absent for a perfectly rigid molecule. Perfectly rigid molecule, if you take very higher frequencies, are generally absent. These are just an information I am giving you. The spectral density at twice the Larmor frequency, 2 omega, is very small for proteins and other molecules. Usually twice the Larmor frequency is very high frequency. The molecules have to rotate very fast. Usually proteins and others are very big molecules. You know that. They are all macromolecules. As a consequence, they cannot undergo rotation faster. The correlation time will be not that much. So as a consequence, correlation takes more time to undergo rotation. As a consequence, spectral density function at twice the Larmor frequency is very small. So this is especially for macromolecules. And the zero frequency also is there, zero frequency component of the spectral density function. It increases with increasing the molecular weight, because the rotational frequency becomes lower and lower as a consequence of that. So zero frequency component of the spectral density function increases. That means if I draw a spectral density function, I can find out how it is changing as a function of molecular weight. We will see that now. The spectral density function depends upon two factors now. One is correlation time, other is resonating frequency. These are the two factors that defines spectral density function. So basically there is an expression for spectral density function, which is given like this. It is simply j omega is twice the correlation time, 1 over 1 plus omega squared tau c squared. This is the expression which has been derived. I am not going into the details of the mathematics because it will take enormous time. That is not the important thing, because you should know what is the spectral density function depends on. It depends upon correlation time and spectrometer frequency, Larmor frequency. And what does it mean? At omega equal to 0, I put this as 0. Then what will happen? Maximum will be there. At omega is equal to 0, then this denominator is only 1. So it implies at omega equal to 0, the spectral density is maximum. Correct? The spectral density, if you for this, it is, you can find out what is the spectral density. When it be put this as 0, you are going to get maximum. That's fine. But then as you keep increasing, changing the spectral, changing the omega, as you start going away, then you have higher and higher frequencies. As a consequence, the spectral density function drops off very fast. So that means how fast it drops off as a function, when this changes, this also depends upon tau c. So these are the two factors which play together. How fast the spectral density function drops off is controlled by tau c. And this is an expression for that. That's what, whatever I said in words is shown in figure here. So at 0, omega is this thing, this is spectral density function is maximum. And you see it starts dropping off. And I have written here 3 different types of graphs. This is a situation when omega tau c is is very much greater than 1. Omega naught is the Larmor frequency, our tau c is the correlation time. When this parameter is very much larger than 1, you get a spectral density function like this. It has a large value here and then drops off very fast. And if you go to a small molecules where there is a fast motion, omega tau c, that means is very much smaller than 1. In which case what is going to happen? See, there is a spread like this and then dropping off is very slow. And in the intermediate situation, omega tau c is approximately equal to 1. This is the graph you are going to get. This is the graph of spectral density function plotted as a function of omega. And when you take omega into tau c together, and this is the graph you are going to get. And this is called a slow motion region. This is a fast motion region for the molecules. So these curve predict how the relaxation traits vary with the correlation time. This will define also the relaxation traits, how it vary as the correlation time changes. This is the graph to understand that. And one thing I want to tell you, the total amount of the oscillating field is always a constant. For example, go in this graph. The total amount of the fluctuating field you are going to get is an area of this, and this, whatever you take. It's constant. It's the total amount of the oscillating field is constant. But the upper limit of the frequency varies with correlation time. Upper limit here is larger here, smaller here, and even smaller here. So, but the area of the curve is okay. Total amount of the oscillating field is constant. The spectral density, that means it represents the probability of finding a fluctuating magnetic moment, magnetic component at any given frequency as a result of motion. What it means is, look at this, what I am trying to say. There is a fluctuating magnetic component of this field that it has a frequency, and as a function of the motion, how it is changing we will come to know here. See, as omega t is changing, spectral density is here for a different frequency, and it will tell you how the magnetic component is there. How do you find out what is the probability of finding a fluctuating magnetic field at any given frequency because of molecular motion, because tau c is embedded into that equation. Basically, if you draw a graph of homonuclear NOE between protons, how it is going to change as a function of omega tau c. Always omega tau c comes as a factor, multiplier. As a function of omega tau c, if you plot the NOE, this is NOE, and the curve appears like this. This is from this journal. Now you can see, forget about this part. This I have not discussed. I will tell you about this is called ROE, not NOE. That is a rotating film over-Raster effect. I will come to that at the end of this talk or maybe in the next lecture. But at the moment, we will concentrate only on the NOE curve. In the NOE curve, you can see this is positive, that is 50%. Positive intensity, when it is there, it is 50%. It goes through 0, comes down and becomes minus 100. That is, the possibility of getting this enhancement in the intensity is plus 50 to minus 100. That is, it can be half of minus 1. That is a possibility of getting the NOE if you draw as a function of omega tau c. If you plot this as a function of NOE, omega tau c, this is NOE. So what does it tell you? For the small molecules here in this region, this is the region pertaining to small molecules. In that region, we say NOE is positive. For a large molecule here in this region, you see large molecules, and also omega tau c is larger here. That means at higher and higher magnetic field. Then what is going to happen? NOE is negative. For small molecules at lower magnetic field, NOE is always positive. For bigger molecule in this region, it is negative. You see, it started coming here, different values. But you can find out a situation where it is this curve is crossing 0 point. That corresponds to omega tau c is approximately 1.1106 or 116. Some number is there. Approximately consider 1. This is a point at which omega tau c equal to 1. There is a switchover point. NOE is 0 here. No NOE at all. Totally 0. So that means depending upon the omega tau c, you can have a positive NOE or negative NOE. That depends upon whether it is a small molecule or large molecule, whether you are doing at high field or at low field. Various parameters are coming into picture. Of course, omega tau c means omega, when I am taking into account, the factor of magnetic field is embedded into it. So this is the important point you should remember. Based on the omega tau c, the NOE can be either positive or negative. So if it is positive for small molecules and negative for large molecules. All right. Going more into the details of that, when omega tau c is very much less than 1, the molecules are tumbling very fast. That's what I said. And that gives a positive NOE. This condition is called extreme narrowing conditions. This is called omega tau c very much smaller than 1 is called extreme narrowing condition. This you can experience only for small molecules, that too in non-viscous solvents. Why non-viscous solvents? Because mobility has to be more. In a viscous solvent, if there is rigidity for the molecule to move, it cannot rotate, tumble very fast. So it has to be in a small molecule, a non-viscous solvents. We have omega 2 is very much smaller than 1. This is called extreme narrowing condition. We can go to another situation. Omega 2 is very much greater than 1. The molecule tumbles very slowly, and there is negative enhancement for this. Here it is a positive NOE, here it is a negative NOE. And this condition is called diffusion limit. It diffuses very slowly. And this can be seen, earlier I said it's for small molecules. Here this omega 2 is very much greater than 1 in the diffusion limit, generally experienced for proteins or macromolecule, big molecules, especially in viscous solvents also. Both in protein and big molecules, and in viscous solvents, when omega 2 will be greater than 1, you will experience this one. Molecules tumble very slow. So extreme narrowing condition for omega 2 is smaller than 1, positive NOE, and small molecules in non-viscous generally, and also in non-viscous solvents. When omega 2 is greater than 1, negative enhancement, diffusion limit, applicable for bigger molecules, macromolecules like proteins, etc., and mostly in viscous solvents. And we go to the next situation. This is omega 2 is approximately equal to 1. In this limit, the NOE goes to 0. When can it happen? It will happen for certain medium sized molecules and at a certain Larmor frequency, because the factor coming into the picture, omega naught into tau c, is the factor. So either of them can be different. Either this can be larger or this can be larger. Doesn't matter. But the product should be approximately equal to 1. So it can happen depending upon certain medium sized molecules, and at certain Larmor frequency this factor becomes 1, and NOE will not be seen in such situations. Okay. Remember we discussed 3 conditions. Omega 2 is very much smaller than 1, omega 2 is very much greater than 1, omega 2 is equal to 1, and omega 2 is when exactly equal to 1, there is no NOE. One is a extreme narrowing limit, other is a diffusion limit. Okay. That all we discussed. Extreme narrowing limit, small molecules, positive NOE, and diffusion limit, big molecules, non-viscous solvents, and negative NOE. That's what we discussed. All right. The zero quantum transitions are thus favored by small molecules. Why? We saw that. See, generally zero quantum transitions are the favorable because of this one. The zero quantum process energy is small, as is the difference in the Larmor frequencies. Only when there is small molecule, generally there will be zero quantum transition probability is more. For double quantum transition energy, the sum of the Larmor frequency is there, omega I, omega 0. These transitions are stimulated by rapid tumbling of the molecules. Molecules undergo rapid tumbling at omega 2, which is equal to sum of the Larmor frequency, which is, as I told you already in the previous class, if the resonating frequency is 500 megahertz, WD is almost 1 gigahertz, close to that. And we can derive all this expression, omega 1, omega 0 and omega 2, all the 3 we can arrive at. Okay, there is an extensive theoretical calculation one can do. But you should remember one more thing in this 3 equations. All of them, of course, we have taken into account the gamma. It could be gamma also takes into account the population distribution, I told you. So if it is homonuclear situation, that is gamma, both are equal. Otherwise, we have heteronuclear gamma I and gamma S. One interesting thing you should observe here is there is tau c at the top, and of course there are 3 factors here coming into the picture, and all of them is inversely proportional to r to the power of 6. R to the power of 6 is coming in the denominator. These 3 equations are arrived at for 3 situations, omega 1, omega 0 and omega 2, all the 3. In the end, so far we discussed about spectral density function, correlation time, varieties of things, diffusion limit, extreme narrowing limit, etc. Now we will go to a situation. Let us say I have done the experiment. I want to get the distance. What is the use of NOE? That's what I told you. It will give you spatial proximity information. So NOE should be, we have to use enhancement in the NOE to arrive at the distance information. How they are dependent on the distance. That's what. Of course, previously I told you 1 over Rij to the power of 6. Let us see that. We know the expression for omega 0, omega 1, W0, W1 and W2. Not omega is larval frequency. Here transition probabilities W0, W1 and W2. They all contain Rij information I showed you in the previous slide. They are all in the denominator Rij to the power of 6. That is there. And this, if I want to consider any dipole, why Rij to the power of 6? You may ask me a question. Of course, we can, logically we can understand this. One can also derive it mathematically. But logically, consider a magnetic strength of a dipole. In the dipole-dipole interaction, it depends upon 1 over Rij to the power of 1 over Rij cube. It is in the denominator. That's why it is written Rij, Ris, whatever it is, to the power of minus 3. But if I have to talk about two magnetic dipoles to have a dipolar interaction, dipole-dipole interaction for NOE, then we need two dipoles. And NOE depends upon two dipoles. Because of that, these W's will depend upon Rij to the power of 6, inverse of Rij to the power of 6. That is what is the dependence of NOE. It depends upon 1 over Rij. Here I have taken heteronuclear, that's why RIS is written. Rij is what normally we talk. Rij to the power of 6, inversely proportional to that. So distance NOE depends upon the distance. So if you know the NOE, we can get distance information. And for omega tau c very much smaller than 1, extreme narrowing condition, I am considering a situation. Omega tau c is very much smaller than 1. All the terms containing omega in the equations for all the three, omega 0, W0, W1 and W2 are negligible. Why? We can see here. Look at this one. This is very much smaller than 1 if you put it. Practically make it 0. Then what is going to happen? This term can be eliminated. Then 3 tau c bar r to the power of 6. That's what it is. This is a situation when omega tau c is very much smaller than 1. When it is very much greater than 1, we cannot ignore this term. That denominator contributes. So this is a situation for all the three W0 and W1 and W2 we calculate for this extreme narrowing condition. Then here also the term, this one goes to 0. We can ignore that. Omega tau c. Both the situation, because omega tau c is very small, both of them, you can ignore it. And again we are going to get 2 tau c to the power of 6. This term goes to 0. Go to omega 2. I'm sorry, W2. Again 12 Tc, this term goes to 0. 12 tau c over r to the power of 6. So we know the transition probabilities, that is W0, W1 and W2, all of them are inversely proportional to r to the power of 6 and of course multiplied by certain tau c's. Now assuming that molecule exists, they exist extreme narrowing consistency, this thing, I substitute these parameters or what we arrived at for all the three, we can substitute in this equation. This is the equation. Remember I told you about enhancement in the signal intensity. This term is called eta. It is enhancement term. If I saturate the spin S, how much is the intensity NOE I gain, I am going to get gain or not, is given by eta. Eta I tells you about the NOE factor when I am irradiating the spin S. And this was the equation given, I told you earlier. Okay, so this is the situation. We will substitute that for all the W's what we arrived at extreme narrowing condition. You substitute for this equation. We got in the previous 2 slides back, I showed you what is W1, W0 as while when we eliminate omega tau c parameter. This is what the terms we got for W2, W0 and this is for W1. We got. Same thing we substitute for this equation. Now you can calculate very easily r to the power of 6 here. If you take it out, here also r to the power of 6 minus 6, take it out, this cancels out. and tau c also gets cancelled out as a common factor. Then what is left here? 12 minus 2, 2 plus 6, 3, 2 into 3 is 6 plus 12. This is the equation you am going to get. What this equation tells me? Eta gain in the intensity. When I irradiate a spin S at the site of I is maximum is half. When? In an extreme narrowing condition. I told you in an extreme narrowing condition the maximum gain in the intensity is half. That is what it is. This can be shown by graphically like this. What will happen when I change the resonating frequency? How it changes? For two homonuclear spins as a function of tumbling rates, these are the tumbling rates, but at different different Larmor frequencies at 200, 400 things. But by and large, it follows same pattern remains same. But only thing is omega tau c is shifted a bit. Okay, depending upon whether what is the tau c. Depending upon the tau c anyway varies, and Larmor frequency we are for a given molecule tau c is kept constant. This one varied. As a consequence, this omega tau c, this position is 0 crossing over is shifting with a different Larmor frequency. This is what is expected because the factor is omega tau c is coming as a multiplying factor. So omega tau c matters when tau c is changing like this because this is also getting changed. All right. Enhancement in homo and heteronuclear case we will find out. For homonuclear case, for example protons, both gamma is same in this expression. Okay. So gamma A is equal to gamma x. I am taking A spin system. What is the maximum NOE you are going to get? 50%, half. What happened in the case of heteronuclear spins? It goes by the ratio of the gamma, because in this heteronuclear case gamma is not same. So gamma ratio comes into picture. See, this is what the factor eta s is equal to this. Remember this thing. This I showed in the previous last two classes also. So if this is equal to this, now this is equal to this half. So in the homonuclear case this is identical, gamma is equal to gamma I. So this is maximum is half. But in the heteronuclear case this we have to take into account. Ratios of the gammas are important, and this is what happens. So for heteronuclear case it goes by the ratio of the gammas. Okay. How much is the enhancement of the intensity you are going to get? Enhancement in the NOE if proton is irradiated. My irradiation spin is, that is gamma eta I into S in this flower bracket S. S is my proton. What is the enhancement in intensity for I? That is for different nuclei. When I irradiate proton, how much gain I am going to get? This is what it is. See, irradiated spin is proton and enhancement signal is, enhancement is seen on the X nuclei. What is X nuclei? There are varieties of nuclei is given here. How much NOE maximum we can get? If I irradiate proton, for lithium nearly 340 times enhancement of the signal. That is really enhanced, large, huge enhancement you are going to get. And go to the case of other carbon 13, 199. That is almost 200%. Intensity gets doubled. Here it gets nearly 3.5 times. Here nitrogen 15, it is 5 times. See, this is the ratio of minus 494 times enhancement. For silicon, of course negative because they are all negative nuclei with negative magnetic moment. Look at this one, rhodium, almost 1600 times enhancement. This is also iron. So depending upon the nuclei in which you are seeing the enhancement, this I am talking about heteronuclei. I am irradiating proton. I want to see what is the enhancement in the other nuclei, heteronuclei, in which case there is a significant advantage if you do NOE. Gain in the signal intensity is enormous. You will see that. That gives a lot of information. NOE gives a lot of information here. Okay. And another important thing, when I was discussing carbon 13, I told you, if you remember, it is an important factor for improving the sensitivity of the low gamma nuclei. For example, when I was doing broadband decoupling of carbon 13, remember I said several ways of decoupling: continuous wave broadband decoupling, gated decoupling, decoupling without this thing, NSA, NOE, all those factors were discussed. In the broadband decoupling, when it is done, when we look at the carbon 13, there is enhancement, NOE, there is enhancement. That's what I told you at that time. There is enhancement in the NOE, which I said I will discuss later. This is the reason. When you do decouple proton, observe carbon 13, there is an enhancement in the intensity by nearly 2 times. That's 200%. And you can see that here. Gamma A into gamma X, gamma over 1 over 2X. I saturate A spin and observe the gain in the X spin. X is the observation. The total intensity is given by this equation. I naught is the original intensity. That's what 1 plus eta is the factor of, that is the gain, total intensity. When I am decoupling proton, this just substitute here, it turns out to be 2. That means I am observing carbon 13, I am decoupling proton, and this is the enhancement in the intensity, nearly 200%. That means twice the signal enhancement will be there. All right. Instead of that, if I see proton, what will happen? We will see that. Of course, enhancement is given on the proton when 13C is decoupled. Remember, now it is reversed. In the previous example, I observed carbon 13, decoupled proton, but here I am doing the reverse. I am decoupling carbon 13, observed proton. So, in our expression, in the whatever the nuclei which is there in the flower bracket, that gets changed. Here it gets changed. Here this is carbon 13, this is proton now, and this is what this intensity you are going to get, about 12.5%. So, remember, even in the case of detecting proton, there is a gain in the intensity on the proton signal when we decouple carbon 13. When we observe carbon 13 decouple proton, then 200% gain in the intensity, but here only 12.5% when I decouple carbon 13. That is because of the gamma, and that factor is there. That is what I discussed. Okay. In the NOE, so far we discussed a lot. How we get the gain in the intensity, everything we understood. Various factors that affects NOE. That also we in this class we discussed a lot about omega tau c, correlation time. What is the omega tau c very much less than 1, extreme narrowing limit. Omega tau c very much greater than 1, it is a diffusion limit. Omega tau c approximately equal to 1, there is a limit where there is no NOE. Varieties of things we discussed, and what tau c correlates, what it defines about the tumbling motion of the molecule. And tau c depends upon the molecular weight and the sluggishness of the molecule, how it is rotating. Everything we understood. And of course, I also showed a couple of equations for the transition probabilities of W0, W1 and W2. When we substituted that in the enhancement in the intensity, where W2 minus W0, W2 plus 2 Wi, all those, the expression is there for the enhancement of the intensity. That is a Solomon equation, which I discussed a couple of classes before. When we substitute this, the parameters W1, W2, W0 for in the Solomon equations, for homonuclear case, we showed that maximum gain is half in the extreme narrowing limit. When there are different heteronuclei present, it goes by the ratios of the gamma. And we saw several examples to see when we radiate proton, how much gain is there in different nuclei. Basically, what is important is when we are looking at the carbon 13 NMR, we detect carbon 13 while decoupling proton. That is where NOE factor comes into picture. When that is done, I showed you there is 200% gain in the intensity. Enhancement intensity is almost each week will be doubled. Whereas, if I decouple carbon 13 and observe proton, there is 12.5% enhancement in the intensity. So, these are all some of the important things about NOE we discussed. NOE is a very, very important factor to get this thing, spatial proximity. When I told you about it depends upon Rij, that means if you know the intensity, if you know the NOE factor from the NOE gain, we can correlate it to the distance. So, we can get distance information. So far, that is what we discussed. Since the time is getting up, I am going to stop here. But doing this, telling this is easy, but there will be a lot of complications involved in NOE. We will discuss that in the next class. Thank you.